Hi, welcome to Knowledge Quest 13 on helical coil springs. To start out, take a moment to read the short article posted on Canvas to be able to identify each of the 4 different types of springs commonly used, their main function, and an example of how each type might be used. And in our class, our focus will be on coiled helical springs. Some top-level information about coil springs: they essentially work by resisting their extension or compression. In this process, they absorb energy, store it, and later release it. Common examples are the springs in a garage, often used to counteract the weight of gravity to allow you to lift the garage door open or help offset some of the power needed by the motor to lift it up. Coil springs in your mattress are another example. The springs in a ballpoint pen and the coil springs in your car are all common examples. So coil springs in your car are also called suspension springs. They're made with wide gap coils that compress to absorb impact when tires roll over rough terrain. Along with struts, they also give your car its height and keep it off the ground. So in most vehicles, you'll find spring shocks and struts working together. We're going to watch a quick video to understand the basic difference between a shock and a strut.
A car that bounces as you go down the road can be very tiring and very annoying. And keeping it from bouncing is the job of the shock absorbers or the struts, whichever your car happens to have. Now, the way you test them is a couple times a year. You go around each corner of the car and bounce it up and down like I did this one. And what's going to happen is it's going to go like this. You let go of it in the down position, and if the shock or strut on that corner of the car is good, it'll come back to the center and it will stop. It won't continue to bounce. If it continues to bounce, probably you need new shocks or struts. But what's the difference between a shock absorber and a strut? Well, here we have an example of a strut. Now, what this does is it has a shock absorber in the middle, and then around it, it has a spring to support the weight of the vehicle. A shock absorber, on the other hand, such as we have here, these shocks do not have the springs on them. They have nothing to do with the height of the vehicle or anything like that. The only thing they do is to keep the car from bouncing. The spring is mounted someplace away from the shock. Now, a shock or a strut, whichever it is, all they do is convert the vertical movement of the car into heat energy. They dampen it so that you don't go down the road just kind of this motorboat effect floating along. Now, if you have bad shocks or struts, and they can wear out in as little as 50,000 miles, or it may be 150,000, but you should check them 2 or 3 times a year. And when they're bad, replace them in pairs, 2 fronts or 2 rears. Now, here's the thing. This shock right here, this one is worn out. If we push this down, we see that it comes back virtually immediately. Now, over here, we have a brand new one. This gives you an idea as to what these things do. As you see, this comes back very slowly. It's very controlled, and that's how it controls the ride of your vehicle. So, check them on a regular basis, replace in pairs when necessary, and remember that if you don't replace them, you could have a dangerous car. That's number 1. But number 2, you could have severe tire wear problems as the result of a bad shock or strut.
So let's talk about the stresses in helical springs. A round wire helical compression spring can develop shear stress due to direct shear force, shown here as F, and a torsional moment or a twisting of the spring wire. These 2 shear stresses can be combined into one shear stress in helical springs. It's given as a pretty simple formula. I won't go into how this formula is derived, but it's tau equals kb over 8fd over pi d cubed. And let's talk about what all these parameters are. Kb is basically a stress correction factor to account for higher stresses that occur along the inner surface of the spring coil as compared to the outer surface of the spring coil. So within Kb, there's another variable C. So C is a measure of coil curvature. and the preferred range is between 4 and 12. And we'll talk more about why that is a preferred range when we talk about spring design. So D, this is the mean coil diameter, and this is really important. So it is not the outer spring diameter, nor is it the inner spring diameter. It is the in-between mean coil diameter. So from the middle of the coil on one side to the middle of the coil on the other side. D, little d, is the wire diameter itself. And then C is the ratio, mean coil diameter over wire diameter. So deflection of helical springs, we are all very familiar with Hooke's law by this point, and of course it applies to springs as well. So the spring rate, also called the scale of the spring, is K equals F over Y, where F is the applied force and Y is the deflection. Formula for the spring rate is about equal to the wire diameter to the fourth times the modulus of rigidity over 8 times the mean diameter cubed times n. And here n is NA, which is the number of active coils. The active coils are basically the coils that are within the spring, meaning not part of the ends of the spring. Another way to think about active coils is that they are the coils that have room to deflect, hence absorbing the applied force. The compression spring shown in blue and gray has 4 active coils and 6 total coils. And you can see that by counting. The tension spring shown in red and gray has 4 active coils. So the type of end on a spring is really important, and there are 4 types of ends used for compression springs. The type of end affects the number of coils and the spring length. So this table here should go in your analysis tool. So a spring with plain ends is basically like a long spring cut into sections without changing the ends at all. A spring with squared or closed ends is one in which the spring angle, also called the helix angle, has been deformed to 0 at the ends. So see how we have this helix angle as we move along the spring, but then at the ends that angle has been brought in or deformed, so now it is 0. So that would be a squared or closed end. A spring with squared and ground ends is one where the helix angle has been deformed to 0 and the end of the spring has also been ground so that it is flat. For important applications, squared and ground ends are preferred because a better load transfer is obtained when you have this nice flat platform. Lastly, a plain end that is ground is one where the helix angle hasn't been deformed to 0 at the ends, but the ends have been ground flat. Sometimes springs will be preset, which is a manufacturing process used to induce useful residual stresses in the spring, thus increasing the strength of the spring. Setting can increase the static load capacity of a spring by 45 to 65% and double the spring's energy storage capacity per pound of the material. But not all commercial springs are set, as this increases their cost. So how is it done? It's done by making the spring about 30% longer than it is needed, and then compressing the spring to its solid height. So this is a presetting machine here. So you compress it to its solid height so that there are no gaps between the coils. All the coils are touching each other and yielding the material in the same direction as the stress is applied in service will. So the spring loses some of its initial length, which is why it was made longer than needed in the first place, but it gains in strength due to these residual stresses. This should not be used for a compression spring that might be used in tension and vice versa. This is because the residual stresses induced by presetting are arranged to be useful in one direction only. Spring stability. You've learned how columns will buckle when the load reaches the critical buckling load, and we've also learned how fasteners in compression can also buckle, for example, a C-clamp. Similarly, a compression coil spring can buckle when the deflection becomes too large. But sometimes springs are designed to buckle. For example, a buckling spring is a type of key switch mechanism. So when the key is tapped by the user, it provides auditory and tactile feedback to the user. And also when it buckles, it strikes an electrical contact which registers the key press. So for steels, we want to keep the free length of the spring less than 2.63 times the mean diameter over alpha, and alpha is just an end condition constant. So the best end condition, meaning the condition that would allow us to have the longest spring possible, would be a spring supported between flat parallel surfaces that are squared and ground. So spring materials is chapter 10.6. If you have the 10th edition, it might be the same in the 11th edition of Shigley, but it's a pretty interesting chapter. So you're going to read and answer some questions on the quiz pertaining to the following. What materials are commonly available for manufacturing springs? And how does a spring's tensile strength vary with wire diameter, material, and processing? What material has the highest tensile strength and is the most widely used for small springs? And how are the ultimate tensile strength and the torsional yield strength related? So you'll have a spring analysis concept check on the quiz. So I know we haven't talked in depth about the solid length versus the free length and what strength we compare the stress to find the factor of safety. So that's why I'm suggesting that you work through example 10.1 in the text before you start this problem. And then next I'll show you my analysis tool. I have a spring analysis section and then a spring design section. So right now you should just start building your spring analysis section. So the areas I have: determining coil curvature and stress correction factor, determining torsional shear stress due to applied load, and determining spring constant K are shown on the left, and then entering wire material properties is a box on the right. So I have this for example 10.1, and I guess I'll just kind of step through it. So we have a helical compression spring made of number 16 music wire. So for number 16 music wire, you have to go to table A28 in the appendix to get the wire diameter D. It's specified in terms of its gauge, which is number 16. So if you do that, you'd find that number 16 music wire is 0.037 inches. You need these constants A and M to estimate the ultimate tensile strength. So you see up here, SUT equals A over DM. So for music wire, if we are in English units, A is 201, and then M is 0.145. So that gives us an ultimate tensile strength of 324 kpsi. This F is from table 10.6, the maximum allowable torsional stresses for helical compression springs in static application. So this is essentially how we relate the ultimate tensile strength to the maximum allowable torsional stress. So for music wire, we don't have anything about the spring being preset, so 45%. So that's what this little F is, 0.45. So the torsional yield strength of this wire is 145.9 kpsi. Next, it's asking estimate the static load corresponding to the yield strength. So for that, I'm going to use this area here, determining torsional shear stress due to the applied load. The first thing I have to find is KB, so I did that up here. And then to find KB, you have to find the coil curvature, which again is just a ratio of the mean diameter divided by the wire diameter. I'm going to pause here. So given in the problem statement, we have an outside coil diameter of 7/16 inches. So to get the mean diameter, we subtract one wire diameter from the outside diameter, and that gives us the mean diameter. So our C would be 10.82 and our KB 1.124. So I have that 1.124 that's automatically brought down here along with the mean diameter and the wire diameter. And then how did I get this F? I got it through goal seeking. So let's say that this F had been something else, like 10 pounds. So that would give me a shear stress that is higher than the allowable shear stress. So I did data, what if analysis goal seek. So set cell torsional shear stress to the value of the torsional yield strength, which is 145.9 by changing cell F. Oops, I did the units wrong. I'm going to do it again. Data what if analysis goal seek. Set the cell. See here, I'm working in PSI, so you got to keep your units straight. So I'm going to do 145,900 by changing cell F. Okay, so 6.45 pounds. So that's the static load that would presumably bring us up to the capacity of this spring. Next, determine the scale of the spring, in other words, the spring constant. So again, you need the wire diameter, the mean diameter. You need the modulus of rigidity. So that's table 10.5, and we have music wire We have a wire diameter that's in between 0.033 and 0.063. So our modulus of rigidity is 11.85 MPSI. And then to get this all to work out, I have my units entered in PSI. So we would just do 11.85 e to the 6th. That just adds 6 zeros. Okay, so this active coils. We are given that this spring has 12.5 total turns, but we need to find the number of active coils in order to determine the spring constant K. So that is another table. It's this type of spring ends table. So I just have a little box that I can move. We're told that we have squared ends, and we want the number of active coils. So we have 12.5 total coils. So if we subtract 2 from that, we would get the number of active coils. 12.5 minus 2 is 10.5 active coils. And then K, the spring constant, is 4.12 pound-inches. So probably the trickiest thing about building this whole table is just deciding what units you want. I didn't want to make 2 separate sections, so I just have this compatible for both English and metric units, but I have to enter everything in the way that it's shown in the boxes for it to work out. Next, estimate the deflection that would be caused by the load in part B. So I don't have a special section in my analysis tool. You can obviously add it if you want, but this is easy enough just to do by hand. So we know that the spring constant equals the force over the deflection. So y equals F over K. Again, just keep track of your units. So 6.446 pounds divided by our spring constant, 4.12 pound force inches. The inches will pop up on top. 1.565 inches. So that's the deflection that would be caused by the 6.446 pounds. Next, estimate the solid length of the spring. So the solid length of the spring is when, well, it's going to be impossible to draw, but when all the coils are touching each other. The free length of the spring is when there's no load applied to it and it's just allowed to stand freely. So this would be the solid length. This would be the free length. So to estimate the solid length of the spring, we go back to this table here. So for squared or closed ends, the solid length LS is D times NT plus 1. So LS equals D times NT plus 1. Our wire diameter, 0.037. And then we had 12.5 total turns plus 1. So we get 0.4995 or 0.5. So that's the closed or the solid length when all of the coils are touching. The next question, what length should the spring be to ensure that when it is compressed solid and then released, there will be no permanent change in the free length? I think what that's saying is that we want to make sure we don't have any permanent deformation in the spring, so we want to keep the stress below the torsional yield strength. In other words, we don't want to apply more than 6.446 pounds because that is the force that brought us up to the torsional yield strength. So if that is our force, we already solved for the deflection from that force using the spring constant. So we'd already solved for this. So Y max, remember, was 6.446 pounds over 4.12. So this is how much the spring can deform before it reaches its torsional yield strength. And then we add on to that the closed height or the solid height, which we found to be 0.5. So that gives us a free length of 2.065 inches. Then given the length found in part F, is buckling a possibility? So, well, look at that. Just appeared in my analysis tool, the spring stability part that you should also add. So the mean diameter, alpha, I got that from the table 0.5. So the critical free length is 2.107. So that's just slightly above what we found for the actual free length. This would be the length that we would want to limit the spring to in order to avoid buckling. And I like what the textbook says here. It says mathematically a free length of 2.06 inches is less than 2.10 inches and buckling is unlikely. However, the forming of the ends will control how close alpha is to 0.05. So I think that's good advice. You have to take it with a grain of salt. This has to be investigated, and an inside rod or exterior tube or hole may be needed to support the spring. And on your homework, you'll design a spring where it has to fit over a rod and then fit inside a hole, presumably to avoid buckling.